Exercise 4.34. Let x, y, and z be topological spaces. Prove that the three product spaces, x times y times z, where first we group together x and y, and then we group together y and z, and then we group nothing at all. Prove that these three product spaces are homeomorphic to each other. Okay, well, so basically parentheses don't matter is the point. Okay, so it's not too surprising that these would be sort of equivalent sets. It's a little bit more subtle that their topologies are the same. And the reason is that, okay, they get their topologies from the product topology. And so, for example, a basis element for topology on this space would be any open set in x times y times some open set in z, right? And that open set in x times y could be any union of open in x times open in y, okay? Whereas a base element of this space in the product topology would be just open in x times open in y times open in z. Okay, so there's a lot fewer base elements for this topology than there are for either of these other two. And the basis for this topology is quite different from the one for this topology. So we have three very different bases, but it turns out that they're going to generate sort of equivalent topologies anyway. Okay, so that's what we want to check. So what I'm going to do is show that x times y times z is homeomorphic to this one with x and y grouped together. And you could do something quite similar for the same thing with the y and z grouped together. Okay, so I'm going to construct a homeomorphism from this space to this space, and it's going to be given by just the simplest thing you can imagine. X, y, z goes to x, y, z, and the only thing to note here is that the output has to be an ordered pair where the first coordinate is in x times y, so this is the first coordinate of the ordered pair, and then the second coordinate has to be in z. So that would be the z here. Okay. This f clearly has an inverse function, where f inverse just takes the output and gives you back the input. So no problem there. All we have to do is show that f and f inverse are both continuous. And then we'll know it's a homeomorphism. All right, so I put a couple theorems up here. I'm going to use theorem 4.6 to show that f is continuous, and then theorem 4.3 to show that f inverse is continuous. Just seemed to work out easiest that way. So first we show that f is continuous using theorem 4.6. Okay, so this is sort of the local characterization of continuity, right? We're looking near a point x in the domain x. So suppose we are given, well, in our case the domain is this sort of triple product. So a point in there would be x, y, z, and we're supposed to take a neighborhood of its image. Up here that neighborhood is called v. I'm going to call it w so I can save my v. So neighborhood w of f of this point, which by the way is equal to x, y, z, like so. All right, and now remember, I have to show that there exists some neighborhood of this point which maps into this neighborhood w under f. Okay, well, I'm not going to show that directly. Instead, I'm going to show that it maps into some basis element which is contained in w. Right. So what would that be? Well, for w to be open in this space means that given any point in w, for example this one, I can find a base element which contains this point and is contained in w. Okay, so then there exists a basis element u times v of x times y times z containing, whoops, the point x, y, z, and contained in w. And then here's the key part with u open in the first half of this outside product, right, in x times y, and v open in z. Oops. Okay, so u is open in the first factor and v is open in the second factor. Good. Well, what does it mean that u is open in x times y? We can take this a step further. It means that, well, let's write it down. Furthermore, there exists a basis element, let's call it u1 times u2 of x times y with, well, the point xy contained in u1 times u2, which itself is contained in u. Okay, and leaving it implicit here that u1 is an open subset of x and u2 is an open subset of y. Right. Okay, well, putting these statements together, we have what? Well, we're interested in this point here. So x, y, z is, well, x, y is in u1 times u2. Okay, so this is in u1 times u2 times, and then z we know is in z, right? I'm sorry, that's not what I mean. What do I mean? That u times v contains this point, so z is actually in v. Okay, so that is a v. And okay, we got that by looking for sort of a nice subset of u times v, which was in turn a subset of w. Good. Okay, well, let's just write that in a different way. This is basically what we need. Okay, then for the neighborhood u1 times u2 times v of x, y, z in our domain, right, in x times y times z, we have f of that neighborhood. That's going to be the special one we were looking for, is equal to, well, this, right? Remember how f's defined. If you take any x, y, z in here, it means x is in u1, y is in u2, and z is in v. So your output is going to be just in the right form to be in this product. And, well, as we noted up here, that's a subset of w. Okay. So we're done showing that f's continuous. We've found the neighborhood u1 cross u2 cross v of the original point in our domain, such that when you apply f to it, you get a subset of the neighborhood w of your output. Okay, well, that's a little hard to wrap your mind around, but hopefully we can at least understand it step by step. It's a lot easier showing that f inverse is continuous, okay, because this time the domain has a bunch more open sets, so don't have to work as hard. All right, so now we show that F inverse from x times y times z to x times y times z is continuous. And I'm going to use the other theorem this time, 4.3, okay, which is a lot like the original definition of continuity, but it says you don't have to check that the preimage of every open is open. It's enough to just check that the preimage of every basis element is open. Okay. So what do we have to say? Well, okay, so given any basis element of our target, right? So it's going to be something like u times v times w of, I'm tired of typing that, let me copy it down here, of x times y times z. We immediately see that its preimage, which, you know, it's going to be in that other form with the parentheses. So u times v times w is open simply by definition of the product topology on the domain here. Okay. All right, so we took a basis element of this product space, and this is preimage, and okay, well the basis elements of this product are any open set of x times y, and u times v certainly qualifies. It's a basis element for the product topology on x times y. Okay, and then we have to multiply that open set by some open subset of z, which w is. Good. So we took a base element of our target, preimage, ends up being a base element in this case of the domain. And so we've checked the condition in theorem 4.3. Good. So that finishes the proof that these two spaces are homeomorphic. So just let me say the proof that x times y times z and x times y times z are homeomorphic is totally analogous to this. And then, well, what if you wanted to show that the two with two different ones with parentheses in them are homeomorphic? Let's say finally we can compose homeomorphisms. Let's do some copy and paste here. We could go from, let's say, there to that one, which would be our F inverse from up here. Remember, if F is a homeomorphism, then F inverse certainly is too. And then, supposing we've proven that these two spaces are homeomorphic, we could compose with a homeomorphism to this space. Okay. Well, and then we have the composition of two homeomorphisms. It's certainly homeomorphic, right? The composition of continuous functions is continuous, and composition of two invertible functions has an inverse. And okay, the inverse is going to be composition of two continuous inverses, so it's going to be continuous as well. All right, so we can do that to see that this space and the other one with parentheses are homeomorphic. Okay. Basically, we did one edge of the triangle up here in both directions, and then I'm saying You can prove another edge of the triangle in a very analogous way. And then to get the third edge, you just sort of trace along the two that you already know. And that does it. It shows all three of these spaces are homeomorphic.